Okay, so here I've set up my muscle fiber. So this is the cell. Outside of the cell, we find sodium. So that sodium causes the outside of the cell to be positive compared to the inside of the cell. Outside of the cell, I also have a motor neuron. So this is a nerve. Inside of it, we'll find the neurotransmitter acetylcholine. Over here on the side, I have my sarcoplasmic reticulum. I'm just going to say sarretic. And inside of that, we have our calcium. So again, we've already identified the thin fibers as actin, and on the actin we find the protein called troponin. And then in the middle we have our myosin. So there's other components involved with the sliding filament theory, like tropomyosin and ADP and ATP, but these are the only parts that I'm going to talk about in my demonstration. So what is the first thing that happens in our sliding filament theory? We have to tell the muscle cell to do something. How are we going to get that communication from our brain to our leg, for example? A motor nerve will have to send the signal via a chemical transmitter called acetylcholine. So when acetylcholine is released, it binds to the sarcolemma. So just a reminder, the outside of the membrane is called the sarcolemma. So the sarcolemma binds acetylcholine, and that is what we have here. And what does that cause to happen? It causes these channels, or yeah, let's call them channels. It causes these channels on the sarcolemma to open up and allow sodium to rush into the cell. So sodium comes into the cell, and with it brings its positive charge. That positive charge, this now becomes a domino effect. That positive charge causes the next channel to open, and sodium comes in, bringing its positive charge. And like I said, it's a domino, so this continues on down the full length of the membrane. So once it gets down the full length of the membrane, so I initiated the action potential here, and it was propagated, it spread. Once that positive charge reaches the sarcoplasmic reticulum is stimulated to release calcium ions. So inside here, I'm going to release calcium ions. So where are they going to go? So that's my sarcoplasmic reticulum. So calcium ions will bind to troponin. So everything is cause and effect. Sodium came in. Sodium caused a positive charge, which is an action potential. The action potential caused the sarcoplasmic reticulum to release calcium. Calcium bound to troponin. So what happens now? The troponin changes shape. So right now, troponin is guarding the binding site on actin, so myosin can't bind. When calcium binds to troponin and troponin changes its shape, it moves off of the binding site, uncovering the binding site. Now it's available for binding. We don't have a way of drawing in, well, we have a way of drawing in. We don't have something demonstrating the myosin heads. So the myosin heads now can bind where troponin once was. And what it does is kind of like a tug of war. It pulls the actin in towards the middle. So notice my H zone has disappeared. My A band has not changed. My I band has gotten smaller, and my Z lines have come together. So the entire muscle sarcomere has shortened, and you have sarcomeres laying end to end to end to end to end to end down this fiber, which causes the entire muscle to disappear. Now you need relaxation. So acetylcholine is degraded by the enzyme acetylcholine esterase or choline esterase or ACH-ACE. Remember, enzymes end in ASE, and the first part tells you what it does. So if acetylcholine is gone, what can no longer be in the cell? Sodium. So sodium rushes back out. The outside once again becomes positive compared to the inside. So if sodium's not in the cell, what can no longer be out and about mixing with other chemicals? Calcium. So calcium has to go back into its sarcoplasmic reticulum. So now that calcium is no longer out and about, what change has to be unchanged? Troponin will go back onto the binding sites. Since the binding sites are now covered, what can't happen? Myosin can't bind, so actin will go back to its original position, and your muscles have now relaxed. So that's the sliding filament theory.